Welcome to the explainer. You know how some apps just fly while others feel like they're crawling through mud? Well, a lot of that comes down to one thing: how they find data. Today, we're going to uncover the secret behind database speed by telling a tale of two queries, one that takes the long road and one that knows a brilliant shortcut.
So here's how we're going to break this down. We'll start with how we think data is stored. Then we'll run a search the slow, painful way. After that, we'll reveal the simple yet powerful trick that makes it all lightning fast. Let's dive in. Okay, so first things first. Let's talk about how we as people see data. We like it neat, we like it organized, we like a logical table.
Yeah, something just like this. An employee table all laid out in perfect rows and columns. It's clean, it's intuitive, but here's the catch. This is just an illusion for our benefit. On the actual hard drive, the data doesn't look like this at all.
All right, now for the fun part. Let's give our database a really simple job. Find one specific employee in this table.
We're on a quest to find the employee with an ID of exactly 10,000. Now, if our database doesn't have any help, any kind of guide, it only has one way to do this: the brute force way. So, how does it actually work? Well, remember that neat table? On the desk, it's actually just a big, jumbled pile of data called a heap. It's totally unordered. And this heap is broken up into smaller chunks called pages. Without a map, the database has no choice but to start at the beginning and read every single page, one by one.
So it starts at the beginning. It reads page 0. Nope, not here. Okay, let's read page 1. Still nothing. And it just keeps going like this, page after agonizing page, until finally, way down on the very last page, page 333, it finds our employee. This whole process is called a full table scan, and it is just brutal.
So let's talk about the real cost here, because it's not really about time. It's about something much, much more expensive for a database.
The cost was 333. That number represents 333 separate trips the database had to make to the disk to read data. In the database world, we call each one of those trips an I/O operation. And this right here, this is the most important thing to get. I/O, input-output, is the biggest, baddest bottleneck in pretty much any database. Physically pulling data from a spinning disk is just painfully slow compared to doing stuff in memory. So the name of the game, the entire goal of performance tuning, is to keep those I/O operations to an absolute minimum.
Okay, reading 333 pages one by one is not a good plan. It's unbelievably inefficient. So there has to be a better way, right? How do we find what we're looking for without reading the entire novel from start to finish?
Well, the answer is we build a map, a shortcut that tells the database exactly where to go so it doesn't have to wander around aimlessly.
And this map has a name. It's called an index. Now, an index is a totally separate data structure. It's small, it's highly optimized, and most importantly, it's sorted. It only stores two key things: the value you're searching for, in our case, the employee ID, and a pointer, which is basically the exact address of where that employee's full record is sitting in that big, messy heap. All right, round 2. Let's run that exact same query again, but this time we have our secret weapon, the index.
And wow, what a difference. The whole process is completely changed. First, the database does just one I/O operation to look at the tiny index. Since it's sorted, finding employee ID 10,000 is practically instant. The index says, hey, the data you want is on page 333. So for its second move, the database performs just one more I/O operation to jump directly to page 333 and grab the row. That's it. We're done. No more scanning.
So let's put these side by side. The payoff is just incredible. We went from a brute force full table scan that cost us 333 disk reads to a super targeted index seek that cost us only 2. From 333 down to 2. That's not a small tweak. That's a performance boost of more than 160 times. That right there is the magic of a database index. And look, this isn't just some abstract concept from a computer science class. This is the absolute bedrock principle that high-performance database systems are built on. So why does this matter to you? Because if you understand how to minimize I/O, you can build way faster, more scalable applications. Now, there are different flavors of indexes. A clustered index, for example, actually sorts the physical data in the table itself, which makes lookups even zippier. And this is why a table's primary key, that unique ID for every single row, is almost always a clustered index by default.
It's also kind of cool to see how different databases solve this problem. For instance, MySQL's InnoDB engine basically organizes the entire table around that primary key index. In contrast, Postgres keeps its indexes separate, and they just point directly to the physical spot on the disk. They're just different engineering trade-offs, but they are both chasing the exact same goal: avoid that horrible, slow, full table scan at all costs.
So the next time you're using a slow app or waiting for a website to load, you'll know what might be happening under the hood. You can ask yourself, I wonder if they're missing an index. The secret to speed, it turns out, isn't some kind of dark magic. It's just about having a really, really good map. Thanks for watching.